So, scanning electron microscopy, or SEM. And when I'm, from this point forward, E minus is electron.
Mm-hmm.
Any of the words feel familiar to you?
Electron, scanning, and then microscopy kind of just sounds like microscope.
It is, yes,
Okay,
exactly.
perfect.
So we've got a microscope that uses, instead of visible light like you would have with like a normal microscope, we have an electron microscope. So instead of light, we're swapping in electrons. The benefit of electrons is that electrons are significantly smaller than a wavelength of light. So we can resolve things that are quite a bit smaller than we could with light. Imagine we're trying to see something like super duper tiny, and I've got this big wave of light. Like, it's not gonna notice that tiny little particle at all. Where if I have an electron, it can hit and bounce back because electrons are super tiny. So that's kind of the principle of what we're doing here. And then scanning, the easiest way to describe this is very old, like, video games. Have you ever seen like a 90s era video game where the screen loads? So we've got like the screen here. The screen loads like this.
Yes.
Where it like starts in one corner and like load.
Yeah.
You've seen that happen before?
Yeah.
That is called rasterizing.
Yeah. Okay.
That's an important word. I'm not exactly how to spell rasterizing. I know how to spell rasterize, but IZE would just be the rasterize. And that is the process of loading a picture, starting with kind of the top left pixel and loading left to right, and then skipping back to the start, kind of to the left side, and going over. So it's sort of like how we read, right? We start left to right, but we don't go left to right, then right to left, then left to right. We go left to right, jump over, left to right, jump over. And this is actually how an electron microscope scans the surface of our sample. So we're going to go over kind of like all of the things that it does, but it is looking at a specific area on a material, and we start at the top left of our section, and we scan left to right and then jump back to the left and left to right. It's happening so fast that we don't notice with our eyes that back and forth movement on an electron microscope. But it does mean that we're not going to get just like a live image, in quotes. Like, we're not going to just be able to like video camera it unless it's going really fast back and forth.
Okay.
But if you're reading really fast back and forth, you lose some resolution. It looks worse.
Okay.
So the whole time we're using an electron microscope, it is rasterizing, so it's back and forth and back and forth. There's another kind of electron microscope. You can also use something called a transmission. Electron microscope, it has the same E and M, so I'm not going to write those out. But a transmission electron microscope, or TEM, I'll put a little, so that's clear. Instead of scanning back and forth like our eyeballs looking at a surface, out of curiosity, when our eyes look at something, the light coming off the surface back to our eyes, is that transmission or reflection?
Off of the surface or into
Off of the surface, that's reflection. Yep. So our eyes in a scanning electron microscope, they see the reflection of the electrons coming back. Transmission is electrons passing through. So that one doesn't rasterize. That one is just we're spraying electrons through. It's a very thin sample.
Okay.
We don't have a TEM in the MCL. The NanoFab has a TEM, and lots of other places around do.
Okay.
That's a similar technique as far as some of the things that electrons do, but different enough, like we're not going to bring it into our discussion much.
Okay.
But those are the two main kinds of electron microscopes. One is scanning, one's transmission.
Cool.
Okay. On a scanning electron microscope, let's start by talking about where the electrons come from. So I'm going to draw the whole like electron microscope here. So we start with a filament of some sort. So a filament, just like in a light bulb, is the source of our, whatever we're creating. If you're talking X-rays, we're creating X-rays. If we're talking electron microscope, we're creating electrons. Most common filament type is tungsten.
Okay.
And there's two ways that we can kind of run current through this tungsten. We can get thermionic, and we can get field emission.
Wait, and that's the what?
This is two different ways to get electrons off of a piece of tungsten.
Okay.
Thermionic.
Thermionic.
So we've got ion and therm, both.
Ionic and
Field emission. Yep.
And those are the two ways to get electrons off of
Yes.
filament.
Yep, exactly. Most electron microscopes, and the cheapest way to get electrons off is thermionic.
Okay.
So thermionic is the cheapest, and it requires the least science, you could say. There's all science. But because of that, thermionic is going to be most of the electron microscopes that you interact with in the course of your life as a materials engineer. Field emission is a lot more finicky, and also a lot more precise. It also means it's more expensive.
Okay.
So field emission is the kind of the fancy type, and thermionic is a little more mundane. We have both in our labs. So we have a tabletop SEM in the MCL.
Okay.
That is a thermionic emitter.
Okay.
And then the electron microscope in the cruise center is a field emission microscope.
Big one.
The what?
The big one.
The big one, yep.
Okay.
You will see, and that's a weird sampling, you will see big ones that are thermionic.
Okay.
So don't associate big with thermionic or field emission necessarily. That's just how our instruments line up.
Okay.
But you're right, the bigger electron microscope that we have is that field emission. Either way, what we're doing is we are drawing electrons off of the tungsten filament. With thermionic, we're going to put a voltage and current into the filament. And usually it's kilovolts and milliamps.
Okay.
As far as like the range of voltage and amperage that we're putting through. And we, using that voltage and that amperage, we're kicking electrons off the filament. It's a very aggressive way of removing electrons because we're just forcing them out by a brute voltage and current.
Yeah. Cool. Come on. Oh. All right.
In that case, we get sort of this spray of electrons coming off of the filament. And we sort of have this job of funneling or filtering them to hit the sample in a more predictable way.
Okay.
Because this spray is pretty chaotic. We just got electrons going everywhere.
Okay.
Field emission is more like if you were to imagine an electron vacuum. What we do is we place some positively charged stuff down here, and we put a little current through the tungsten, but we draw the electrons down.
Okay.
Have you heard the word bias when it comes to positives and negatives?
I feel like I have, but I don't really know what it means.
Totally fine. So a bias just means a difference of charge.
Oh.
I have a more positive charge on this side and a more
Okay.
negative charge on this side of whatever system I'm talking about. And so field emission, we're pulling the electrons down with a bias. We've got a
Because
positive.
there's a better charge down there. The
Yep.
bias.
Yep. The electron microscope, or the electrons get pulled off of the tungsten instead of being kicked off the tungsten.
Okay.
The reason field emission is better, you can understand, I would imagine, why that's more expensive. We have to
Yeah, you have to have
we have to
something.
build the
sort.
system to pull that down, and we have to be very controlling of it.
Oh, yeah.
The reason that leads to better image quality is instead of getting this waste of electrons where I'm spraying them all over the place and then filtering
Push it to one
them,
area.
yeah, they come off just a little bit better ordered already.
Yeah.
So when I refine them, I'm refining good to amazing.
Yeah.
Instead of this scattered stuff from thermionic, I'm refining like to good enough.
Yeah. Okay, that makes sense.
So we're going to talk more specifically about thermionic because that's what I know more about. But a lot of the guts are going to be fairly similar. So
Okay.
moving forward, no matter what method we're using, we have now these electrons, and we want to make sure that they come down. Let's say our sample is down here. I want to end up with this. I am so off center here. I want to end up with this really nice kind of like straight beam of electrons, nice and parallel and focused on the surface of the sample.
Okay.
And what I've got in between all of this, so pretty much this whole, from like the filament all the way down to right next to the sample, we call this the column.
Okay.
And if you look at most electron microscopes, you can actually physically see the column. It is literally just a stack of like metal cylinders with stuff sticking out of the sides of them and all of that.
Okay.
And the column is where we're going to refine the X-rays, refine the electrons, get everything like stuck together nicely.
Okay. Refine electrons.
Yep, we're refining the electrons. You might want to make a little more space just so you're aware.
Oh, in this area?
Yeah, we've got sort of this like long stack of things.
Okay. Alright. Alright. Here, you can probably keep going. I think. Oh my god.
Totally fine.
Boom.
Amazing.
Probably better.
The first thing we're going to want to do, compared to an electron, how big is a molecule of air? Whether that's nitrogen, carbon dioxide, oxygen.
Way bigger.
Way bigger. So first thing we're going to do is we're going to remove all of the air from inside the column. Most of the time we're also going to remove air from around the sample. So both
Okay.
the column and the sample are in vacuum. There are some systems which allow not as strong a vacuum around the sample, so your sample doesn't have to be fully evacuated. But either way, the column for sure. We need to pull air out of it.
Okay.
That allows our electrons to travel in that nice straight line once we create it without bumping into air molecules that are going to scatter them around or maybe even absorb those electrons.
Yeah.
So I'm like losing a ton of material as I go. Directly below the tungsten filament, and there are actually, I should specify, there are a couple of other filament types. Lanthanum boride, let's see. I'm pretty sure it's lanthanum board, LAB6. I'm gonna just double check that really quickly. LAB6 requires a little less energy to pull electrons off of, so it is considered better, but also more expensive. Yeah, lanthanum board, LAB6. Okay, we've got our filament. It is throwing off electrons. We are going to stick some little discs in, kind of in the path here. And these are called apertures.
Like on a camera.
Yeah. Do you know the function of an aperture on a camera?
It adjusts the the amount of fuzz in the background.
Hmm.
That's how
Interesting.
I think
Okay.
about it.
Yeah,
Or like it focuses on the thing that you want in the picture rather than something you don't want the majority of the time.
yes. I know more about its like
Functions,
physical.
not
It's
as,
it's
not
physical.
as the
Yeah.
camera stuff.
Yeah. So I was not aware of its final effect, I guess.
Yeah.
What they are doing is they are narrowing or opening the amount of light
Yeah.
coming in. So an aperture is going to like close off or open up.
I probably should have said it that way rather than
No, I
the
mean,
effect.
I have, my field and you have your field. That's
Yeah.
totally fine. The effect is cool. I like learning that.
Yeah.
So these apertures are they're sort of like tiny little donut-shaped discs. They are very, very thin and flat, so they're not rounded like a donut is, but they've got sort of the circular shape, and then they've got a tiny little hole in the middle. And we can have lots of different types of apertures. We can have fixed. And fixed would be like they just sit there. They don't move around. There aren't different sizes. They just are. We can have movable. A movable aperture would be something where we have maybe a plate of aperture or I don't know why that was so dark there. It's kind of this big long plate that has circles in it of different sizes.
That makes sense.
And you can move the plate in and out to get a larger hole or a smaller hole
that
to
makes
narrow
sense.
these electrons down. We also, the very, very last one, I maybe made this a little bit longer than it needed to be for the column. But our very, very last aperture, it's usually right at the very bottom, no matter what other stuff is kind of in the middle. My last is called an objective aperture. Going back to photography, you have an objective lens. Objective aperture in this case is going to be sort of your final.
Set amount.
Yeah,
That you want it to be at to let through.
Yes, it is the final boss battle along this pathway here, where you end up. Yep, it is going to be the smallest hole of the whole column.
Yeah.
And it's going to really just like be the final refining before it hits the sample. There are some other things that you can put in that you can use to kind of like bounce the electrons. So like ideally at this point we've sort of got this like stack of, so that the electrons coming through are just nice and straight. There are things that you can do to sort of like bounce the light back and forth so that it converges on the sample a little bit. I feel like I'm missing something, but I will come back if I remember what it is. And after that objective aperture, we've got that really nice parallel beam that's going to come down and whack our sample.
Yeah. Boom.
Yeah.
Sweet.
Okay, so let's talk about what happens to the electrons at the sample and kind of the detectors that we've got surrounding that setup. So we'll change colors. So we're gonna zoom into the sample. We have 3 big, like, main interactions that are going to happen at the sample surface.
Okay.
The first and kind of the simplest is, I don't want to add like so many colors, but also like I want to separate sections. So the first one is called secondary electrons. And that's going to be written 2 with a little degree symbol. It's not super clear. And the E minus. So we'll also sometimes call this SE for secondary electron. In order to have a secondary electron, it makes sense that we would have a primary electron, and that is the one from the filament itself. So we're going to call this 1 with a little degree symbol, E minus. That's our primary electron. And we're going to draw a really simple model. Here's my nucleus. Here's, I don't think this does shapes as easily as your note taker does.
Boom.
So we've got our various orbitals around a nucleus of an atom, right?
Yeah.
We know that this isn't exactly how atoms look, but it's the easiest way for me to draw it. And this atom has electrons traveling around and around it, right? It's got some on the inside, it's got some on the outside. Which of these electrons is the most solidly attached to the atom?
The closest to
The closest, exactly. And the outside ones are less well attached, and the middle ones are like middle. This primary electron can come in, and among a couple of other things that it can do at the electron, it might bump into, actually let me rearrange these electrons a little bit so that I'm not like messing up my line here. Okay. It's going to come in, it's going to whack one of these electrons traveling around, or get close enough that the electrons' negative charges repulse each other. And this electron right here is going to get kicked out. I'm going to actually change color on that back to my blue, because that is our secondary electron.
Okay.
I'm going to see if I can erase. Oh no, erasing all the wrong things. Beep. That creates sort of this hole.
Yeah.
The primary electron will have lost a little bit of its energy in this collision, so it's probably going to like scatter off in some other direction as well.
Okay.
It is still, you'll notice like I'm drawing straight lines versus curvy lines. This incoming electron has a lot of energy. We either pulled it or kicked it off of the tungsten, and we did that with a strong enough force
It's a break ball.
that, yeah, it's speeding. It's going really fast.
Quick.
It is. When it smacks into the secondary electron, it transfers some of its energy to the secondary electron, but it's unlikely that it transfers all of its energy. So the primary electron is actually going to retain quite a bit of its energy. So I've got the secondary electron drawn as this curvy line because it kind of like falls out. It's not a particularly high energy system, where the primary electron can keep going and actually can run into multiple other atoms and create a bunch of other secondary electrons. So now it might kick out another secondary over here, and then down here it's going to kick out another. So that same primary electron can kick out several secondary electrons from the same material.
Okay. That makes sense.
This secondary electron is pretty low energy, like we talked about. So if I'm to zoom out to the surface of my sample, let's say I have a sample that's not polished really, and I'm getting these electrons kind of kicking out of the surface. Some of them are kicking from within the surface, some on the outside and some kind of deeper inside as this primary electron travels deeper into the sample. I'm getting this kind of creation. Sorry, it kind of looks like worms. That's a little weird. And I'm right-handed, so they're all going to point to the right. But we're getting all of these secondary electrons created from kind of all over the sample here. So what we do is we place a secondary electron detector. Better place to put it would be like here.
Okay.
It is fairly even with the surface of the sample, maybe a little higher than the surface of the sample. Sometimes it's right above the sample, but I'll show you why it's useful to have it kind of off to the side. And it's going to be down kind of low, just like next to everything.
Okay.
And the secondary electron has a positive bias over the front of it. Do you remember what that means?
Yeah.
What's a bias?
So it has a positive bias on this.
Yep, on the front of the detector.
Means that those will go towards it.
It does, exactly. So all of those secondary electrons, they get kicked out of the sample. The ones that have enough energy to exit the surface of the sample get kicked off up into the air. And they're going to start traveling. Why are we doing that? Sorry, sometimes it is so very thick, and I don't want it to be thick. I just want it nice thin. It's going to start traveling toward the detector.
Boom.
Yes. So you drew it in your notes, and I drew it in mine as well. Some of these are going as they, between where they got kicked off and the secondary electron detector, as they're trying to travel along this line, they get intercepted by a piece of the surface. So this electron actually is going to die here inside the material. It's going to be reabsorbed by some other atom that probably lost an when it got whacked with the primary beam.
Sad.
This is going to create sort of this shadowing effect. So let me see if I can do some gray. So these electrons from here are not going to likely get picked up because I've got this big kind of curvy thing. Also, anything kicked out from this surface is not going to get picked up because, again, they're on the kind of the wrong side over here.
Yeah.
Same with over here. We're probably going to get this shadow down inside of this valley here. Maybe a little shadowing here. And that's going to create some contrast.
Yeah.
I've got areas that I'm getting a lot of electrons from, and I've got areas where I'm getting almost no electrons from. And because of that, I have these bright areas and these dark areas.
Bad news.
Do you know the word topography?
Yeah.
This, did that way too far over? I could feel that's what was happening. I'll draw a little like, okay, so the secondary electron detector, because we're getting these sort of shadowy areas and these brighter areas, actually I could, we'll highlight them. We're gonna get a lot of electrons from like these really high spots right here. Because of that, we say the secondary electron detector is best for topography. Most of the information you're going to get from a secondary electron detector is topography.
Okay.
When people, do you know the word topography?
Yeah.
When people talk about electron microscopy, specifically secondary electrons, they will often talk about being in a helicopter. You're kind of looking straight down from above, and let's see. If you are looking straight down from above, it's noon, there's no shadows, you're gonna maybe see like, and then like a road, right? And then like maybe you'll see that there's a tree here or whatever. And you've got this just like, I can see buildings, but they're just like these very two-dimensional structures.
Yeah.
If I take that same thing, but now I take a helicopter ride at sunset when I've got these shadows being cast, I would maybe see that this is like a really, really tall building next to a shed, and this would all be filled in, right? Because it's a shadow.
Yeah.
Where you're like, this is actually just like a small building. And maybe this tree is like, you know, a really like tiny tree because you can see the shadow. But now, even though we're still seeing in 2 dimensions, we're getting 3-dimensional data from that 2-dimensional view.
That makes sense.
So you'll see people talk about this like analogy quite a bit. Similar to the secondary detector. That's why we stick the secondary detector along the side. It's sort of like the sun at sunset where it's it's low and we're creating these shadows, giving us a little bit of that 3-dimensional information while still collecting data in 2 dimensions.
Do they only have it on one side? Because like if it's a sample that's like this and then it's only on one side, I feel like you'd miss a lot of data like if it were on this side.
Yeah, so that is where I was saying at the very beginning of talking about secondary, that like sometimes they have secondary detectors way up high, sometimes they're like way over on the side. There are fancier and fancier microscopes that have multiple secondary detectors.
Okay.
And you can overlay or you can swap from like one view to another.
Okay.
So some of them you can get more of this, or you could swap over to another detector for more of that.
Yeah.
A lot of microscopes also will have a rotational stage. So I could take this sample and I could rotate it around like in kind of the horizontal axis.
Okay.
So that I'm now getting information from the opposite side, and it would be the opposite of what this is.
Okay. That makes sense.
Cool. I wish I had a laser pointer on mine. I just use the select tool and deal with the consequences.
Yeah.
Any other questions about secondary electrons and that sort of setup? Okay, great. Let's talk then in green about one called backscattered. Electrons, we call that BSE typically. And I am going to steal this. Gonna fix it up just a little. boop, because I don't need those. We're back to like primary electron coming in, whacking an atom.
Perfect.
This time though, let's say our electron actually misses all of the secondary electrons and it gets really close to our nucleus. So it comes down and it's attracted to the nucleus, sure, but it's got a lot of forward momentum. So let's imagine let's imagine someone sets you in an office chair and they push you as hard as they can down like a really long hill. Now you're flying. You're in this office chair, you are just going. You have no control. But you see a light post in front of you. You're like, that light post is stationary. I would love to be stationary. I'm going very fast. You stick out your arm, and assuming you've got, shoulders of steel, you grab that light post. What's gonna happen to you?
Lose speed.
You're gonna lose speed, and assuming you can hold on, you can't stop.
That's kinda like, whoop.
Yes, so you're gonna slingshot around that light pole. Slingshot. So it might be flung out to the side. The backscattered electrons we can measure actually get slingshotted directly back up. So they do a full 180 and head straight back the direction they came.
Whoa.
We then, because I can't stick a detector on top of where the electrons are coming from, because that would block my beam and undo what I'm trying to do. So we build what's called a ring detector. And this ring detector goes around where the primary electrons are coming out of the objective aperture. So this is how I tend to draw it, as sort of this ring shape. I've got my label sort of in the way, but sorry,
What the heck?
it's the plants. So that ring detector will just sit really close to where those primary electrons are coming in, so that anything that is slingshotted does that full 180 around the nucleus and comes straight back up. We pick it up. Yep.
Cool.
Thinking about my analogy, let's say you have two options. You're flying down this hill in the office chair. You have, and I'm gonna draw a little divider here because that's kind of what I did above. You have a twig stuck in the dirt. In this analogy, that is a small atom with a pretty small nucleus. Versus you've got a big cemented into the ground light pole. That is a larger atom with a larger nucleus. Which do you think is going to be more sturdy for this slingshotting action?
The second one.
Yep, that big heavy one. So this littler one, we're going to slingshot some back, but not nearly as many as are attracted to and will slingshot from this larger nucleus.
That makes sense.
So what our detector is now seeing is these smaller atoms are going to be darker on the image
That makes sense.
because there are fewer electrons hitting the detector from that element.
Yeah. Interesting. So lighter and darker.
Yes, so the smaller one is going to be darker because dark means we're getting no signal. Black means no signal. So a dark gray, because all of this is grayscale, dark gray means that we're just not getting as much signal back.
Okay.
Where white would mean we're saturating the detector. We're getting a ton of electrons back.
Yeah.
And so heavier elements are going to be brighter on the picture.
Okay.
It's a little bit like you have to think about it while you're running it because your screen is just going to show. So let's say I've got my little like SEM image here and I've got, I don't know, what have I got? I have a gold foil and I have stuck graphite particles on it. Let's say that's what I have. I'm going to have this very bright image with these dark spots on it. And I have to think like, okay, gold is heavier than carbon.
Yeah.
So carbon is darker than gold on backscatter. Right? So while I'm analyzing, I have to actively be thinking about like, okay, what's brighter, what's darker, so that I know what I'm looking at.
Yeah.
There are a couple different ways that you can remember this in like an accessible format. Rough. It's fine. Didn't want to pick up that piece anyway. There's the logical ways, and then there's the stupid way that my brain remembers it, and I'm going to tell you both. And you're going to laugh at the one, and so you're going to remember the stupid way. So welcome.
Perfect.
I think the most scientific way would be to think through this process right here.
Yeah.
That we get more slingshotting from these heavier elements. You also could think about it in sort of like, this isn't a very scientific way, but is sort of logical. Graphite, or things that like carbon is, tends to be black to our eyes. This is visible light, so it's fully different detection system from a backscatter electron detector, but carbon is black. And that's true for backscatter and true for our eyes. So, like one mnemonic, that looks like it says fumonic, but it's fine. Carbon, especially like graphite, is just dark to eyes, and backscatter detector. So like that's one way, not particularly scientific, but I feel like is innate. Here's the stupid way that my brain remembers. Dark is light.
Boom. There it is.
Terrible.
Dark is light.
Dark is light.
That's it.
Because it is when we're talking about the lightness of the element and the darkness of the image.
Yeah.
But it sounds like there's no way. Dark is not light. How stupid can you be, scientist? Anyway, so there you go. Those are my kind of like two mnemonics. That's what works for me. I don't know. It is what it is. Any questions about backscatter electrons there? Good, okay. Now, one more interaction that we are going to talk about, and then we'll talk about material types and what makes for a good or a bad kind of sample. I am going to grab this secondary electron picture again, and I'm actually going to I'm going to change even less of it this time because this next thing that we're going to talk about is actually a subcategory. It happens at the same time as a secondary electron is being created. I have not used orange yet. Oh, I kind of did use orange up here because that was this section. We're going to use, it's not good to use red and green because scientists are colorblind. Purple's fine. This is called, this is called energy, my guy. Dispersive. X-ray. Spectroscopy.
Dang.
Super simple, not a tongue twister in the slightest. Yes. Just like microscopy, spectroscopy is the study of light things. But in spectroscopy, the spectro, do you know the word like spectrum? We're talking about a range of values. Here we are looking at a range of energies, so energy dispersive. And we're studying X-rays. That might feel a little weird because you're like, hey, we're studying electrons actually. Here is what happens. We're using purple. So when this secondary electron pops out of my atom, I am left with a big gaping hole. Do atoms like having holes in their electron orbital filling?
No.
No. They very much prefer to have the inner circles filled before the outer circles. So one of these outer electrons has the ability to drop down. What is it losing when it drops?
Oh my gosh. What is it losing? Is it like it emits a
It does
light?
emit.
Or
It does.
Yeah.
It is losing energy
Yeah.
because it was traveling around the outside. It was traveling really fast to go all the way around the outside, and it's now settling into a more favorable position.
Yeah.
So it's going to lose some energy when it drops down. And on this scale, this like the space between this orbital and that orbital, it's going to emit an X-ray. Which I think you said emit light, which X-ray is a light, the
Perfect.
type of light. So it's not something our eyeballs are going to see, but it is going to happen.
Boom.
And that is happening because that electron really does prefer to be in the inner circle. And this X-ray, the wavelength of the X-ray is specific to this atom and these orbitals. So we call this a characteristic X-ray. Where am I going to put that? A characteristic X-ray specifically means that the wavelength is specific to a certain element. And that element, if we're counting 1, 2, 3, if we're dropping from the third orbital down to the second orbital, which is what I've drawn here, it's going to make that one wavelength of X-ray, and that only. That is the wavelength of this electron dropping down. I'm going to draw something that's way more information than you're ever really going to need, but I'm going to do it anyway, just so that you know like how deep we could go into this. There are some much better pictures in the world than what I am about to draw. nice HTML site here. We'll call that fine enough. So this is, if I've got like I've got an atom here. And, okay. And do you know, have you learned about like quantum numbers?
Yeah.
Sorry, do you want us to close that door?
No, it's okay.
Okay. Quantum numbers say that electrons can't be the exact same energy as each other. They like to be, like even the ones that are really similar in energy, you've got like spin up, spin down.
Yeah.
So every electron has its own energy within an atom. The inner kind of like orbital has one spin up, one spin down. The next outer orbital has, is it four electrons?
Yes.
Which if one is spin up and one is spin down, then we've got like two. I'm trying to draw these as close as I can. We technically have like two orbitals that are like really, really close to each other.
Yeah.
And if we're drawing these orbitals as like, here is 0 energy, and out here is like higher energy. As I move from the center outward, I have like this spectrum of energy, right? And so that I don't have to draw all of the circle, this next orbital actually has like 4 orbitals that are all right on top of each other. And for the sake of like, I'm drawing this kind of stuff, I just draw as if it was one. But in function, we've got these kind of layers. A drop down from any of these layers to the middle layer. So let's say the hole is here. A drop down from any of those, from here to there, or from here to there, we call that a K energy.
Okay. I'm just gonna write that out.
So we call that inner kind of circle the K shell. It is dropping from one shell to the innermost shell. From anywhere, it can come from anywhere, but it's dropping specifically to the innermost shell. And we can even get, this would be a K alpha, and this one would be a K beta. So alpha means 1 level drop. Beta means 2 level drop. And we could even zoom in. This one is a K alpha 1 because it comes from the lower K alpha. And this one would be a K alpha 2. I mean, that's so very tiny. I don't really know how to write that. That isn't going to be tiny, but we're just going to write really tiny. In this case, 1 means from the closer suborbital. And 2 means from the next closest suborbital. Does that make sense?
Yeah.
So, like, again, I'm going deeper into this than really is functionally necessary to operate an SEM. But you will sometimes see things that say K alpha, K beta. And when we talk about X-ray generation for X-ray diffraction, we talk about K alpha 1 and K alpha 2. So all of that language is like wrapped into a whole bunch of other things. So that's why I'm going into it. Next drop is anything that drops to the second orbital is called L. So if we were to call this the K shell, the next would be the L shell, and then the outermost is the M shell. We have the same thing where L alpha, L beta. Actually, I don't know if you could get an. Yeah, you could technically get an L beta if you have a big enough atom. It's unusual, but like technically. And then M shell is going to be, and if anything drops to your third shell. Again, this is only going to happen in really big atoms that have 4 or more shells.
Okay. Okay.
Any questions about that? I know that's like a little deep in the theory there. All of that to say, these values, K alpha 1, K alpha 2, K beta, L alpha 1, L alpha 2, whatever, all of those are considered to be a characteristic X-ray. That wavelength, this K alpha 1, comes only from this element.
Whatever it is.
Yes. So as an example, copper K alpha is 1.5406 angstroms for its wavelength.
Okay.
So like that is, if you see a wavelength that is 1.5406 angstrom, and that is an X-ray, that comes from copper K.
alpha.
There's no one else that makes that exact wavelength. So what we can do, zooming back out to 100, is I can stick an an X-ray detector on this system right here. I can measure the wavelength of this X-ray, and it'll tell me what atoms are present. So, I skipped over this just a little bit. The shorthand for this mess is typically EDXS. It can also be EDX or EDS. Something that you will hear sometimes that it is not is EDAX. EDAX could be like an attempt to pronounce whatever that is. EDAX is a company that makes EDS detectors. So I prefer not to call them EDAXs because actually the three that I run, one is a Thermo Fisher, one is an Oxford, one is a Bruker. None of them were made by EDAX.
Yeah.
So that's just that's the lineup we have here. None of our EDS detectors are EDAX specific. But that is not an acronym for this technique, so I prefer not to call it EDAX specifically.
Okay.
I'm a hypocrite though, I still call them Band-Aids, even though Band-Aid is a company. I still call it Jell-O, even though it's gelatin.
Yeah.
Kleenex versus tissue. We do this. In the spheres of science, I prefer to be more specific. So I prefer not to use EDS. EDS is my go-to. It's just what's been drilled into my tongue. But you'll hear any of these 3 sometimes.
Sweet.
4. You'll hear any of those 4 sometimes.
Okay.
Okay. Any questions about EDS?
Can you combine these in a lot of machines or no?
Every machine has the capability to look at all of them.
Okay.
That was a little bit of a lie. They don't necessarily come pre-installed with all 3 detectors.
But you can.
But if I'm shooting an electron at a thing, all 3 of these are happening, whether I see them or not.
Yeah.
Similar to visible light exists, whether I am blind or not. It's happening. Whether I have the detectors for visible light built in, that's, person to person. So if I'm doing this column stuff, if I'm shooting an electron at a sample, I am creating secondary electrons. And because I'm creating secondary electrons, I am getting characteristic X-rays are being generated. And I also have electrons being backscattered. So those are just happening. Always.
Yes.
There are a couple other fancy detectors that you can stick on an electron microscope, but most of them rely on one of these three principles. I talked about like placement of a secondary electron is going to give you different information.
Mm-hmm.
So you might have a couple secondary detectors, all with different purposes. This EDS detector, you can take a detector and you can have it not care about where the X-rays are coming from, or
Okay.
maybe it does care about where the X-rays are coming from.
Yeah.
Maybe it does care about what angle the X-rays are bouncing off the sample.
Yeah.
Like, there's a lot of different parameters that we can still study, but it's these three principles that are
Okay.
happening. Pop quiz. If I have my secondary detector turned on, are X-rays still being generated?
Yes.
Are backscattered electrons still being generated?
Yes.
Yes. Everything is still being generated.
We're just
Even
not seeing it because we
though,
don't have the sensor for
Yep,
it.
just depending on what detector is what I'm seeing. So that's a different thing. Okay, cool. Just a couple more minutes. Let's do like 5 more minutes. Let's talk about what makes a good or a bad sample. Going back up here to the column, do you remember what environmental condition the column is in?
Vacuum.
Vacuum. Can you give me an example of maybe a sample that would be bad for this technique based on that information?
Water.
Absolutely. Hydrated samples, not great.
Yeah.
That would be biologics, so flowers, leaves, bugs, hydrogels,
Yeah.
paint. Any of those things that have not been dehydrated is going to be not ideal. So I'm gonna put a little like sad face next to hydrated samples, make it really clear. That makes it kind of hard for biologics to be
Yeah.
scanned. So kind of a subsection of that is biologic samples. Biologic samples have an additional struggle. And we'll talk about that in just a second because I want to stay on the hydrated stuff. I will get there. Any guesses on what we can do to improve that situation?
Dry them out.
Dry them out. Freeze drying for these is the most common because freeze drying tends to preserve the structure of a material pretty well. So for both of these, freeze drying would like keep the structure generally, but allow it to go under vacuum. There are also modes where you can do a low vacuum mode.
Okay.
So it's a less strict vacuum, which might preserve like the hydration of the sample. It does reduce our resolution,
Yeah.
but it might help. Cool. I mentioned biologic samples have another problem. Imagine we just, in any circumstance, are throwing electrons at a thing. What do we use electrons for on the daily? Electricity.
Okay.
What happens if I flow electricity through, let's say, a piece of wood? Is that conductive or non-conductive?
Non-conductive.
Non-conductive. And what does that do to the wood? Have you seen those artists? Like put really high voltage
They
through
like.
it? Yeah, it gets all crackly, it burns the wood.
Yeah.
It's trying desperately to find some ground, some place where the
Somewhere,
electrons can
yeah.
flow, but it's not, because it's a conductive material. Biologic samples are also non-conductive, and we are shooting electrons at them. So we end up, if I've got this like biologic sample and I'm shooting electrons at the surface, I end up with this like cloud of electrons just sitting on the surface. And because of that, I'm going to get poor image quality. I might burn the sample.
Yeah.
And my electrons are going to have nowhere to go. So I'm going to end up with like this very staticky sample, just this huge charge buildup. So low conductivity is sad face. Low conductivity can be resolved. Some of the ways that we resolve that would be carbon or gold coating. So we put a little layer of conductive material across the top of your sample.
Okay.
And that allows the electrons to flow across the surface. Now that doesn't do anything to fix the middle of your sample, but at the very least the electrons can maybe move out of the way of incoming electrons. That is the most common kind of way to deal with that. You can also, funnily enough, low vacuum mode. Which sounds a little weird, but basically in low vacuum mode, we've got these like electrons. Here, I'll copy this so I'm not messing with that picture. I have random O2 molecules floating around, and they come down, they pick up extra electrons, becomes O2 slightly negative, and then it can carry that over to, like, let's say this is the wall, and the wall's made out of stainless steel or whatever, and it deposits the electron into whatever grounded source is around, and then it just becomes O2 again. And we have enough of these O2 molecules just like floating around. It's gonna mess up our kind of primary beam here a little bit, but those oxygens sort of work as like a transport shuttle to move the electrons off the surface. It's a little less efficient than like carbon coating, but works surprisingly well for like if you're like, I absolutely cannot coat my material. It works pretty well. So low conductivity is not great, and anything that is not vacuum stable. Those are going to be our biggest nemesis when it comes to preparing a good sample for electron microscopy. We can do solids, we can do powders, we can do fibers. There isn't a lot of structural issues. It has to be small enough to fit in the microscope. And in metallurgy, we'll typically polish the samples instead of sticking them in raw, so that we get sort of a clean, flat surface.
This.
Yeah, so in metallurgy, we don't usually care as much about secondary. We're looking more maybe at like the elemental analysis.
Oh, okay.
Or we like polish it and then we etch it. So we have a very specific like topographical pattern. So that's a little bit more controlled. We call that metallographic preparation. And that's a whole separate conversation. But typically, SEM is good with most things as long as they are not going to struggle with the vacuum and not going to struggle with the conductivity. One little asterisk before we go on this is that not thermionic, the field emission. Some field emission microscopes have magnetic apertures. So materials that are ferromagnetic might not work.
Okay.
So that's just like a little like sub thought is in some field emission, we also have to pay attention to magnetism in addition to conductivity and vacuum stability.
Okay.
There you go. Any questions about electron microscopy as a whole?
No.
Stellar.
Cool.